Today we're going to begin our discussion on nuclear chemistry. This is one of my favorite topics, and it's one of the newer topics in the field of chemistry. This particular science started right around when we figured out what atoms were, and propelled itself very, very quickly within about 50 years, being able to use that technology as a weapon. And we're also using it now as a power source. So very important for you guys to know, and interesting as well. So let's start with a little bit of the history. Radiation was discovered by Henri Becquerel, and he was a French chemist in the late 1800s. Henri Becquerel was doing lots of different experiments and had lots of different chemicals sitting around his lab. He had some uranium salts in a desk drawer, and it just happened to be sitting there alongside some other experiments he was doing. These other experiments involved working with light to make a reaction go. So he had some photographic plates, and you can kind of think of those like old film negatives. And they would be exposed, when you expose them to light, they would create an image of the thing that was on the inside. He had prepared a sample and went to take it outside, but it was cloudy, and so the sun wasn't out. So he took the sample, hoping to save some time, and put it in his desk drawer. When he came back the next morning, he noticed that that sample had already been exposed, as if it had been out in the sunlight, but it had been in a dark desk drawer that entire evening. So he tried to repeat the experiment, and it happened again. So again, what was causing these photographic plates to be exposed? He finally narrowed it down to the uranium salts that were in his desk drawer, and so he gave it the name radiation. There must be something radiating from these uranium salts causing the photographic plates to be exposed. And so that was the name that was given to radiation. It radiates, just like a radiator radiates heat. All right. Now, you may not have known about him, but you've probably heard of his assistant. His assistant was Marie Curie, and later her husband Pierre joined the task force, and they made several breakthroughs in the study of radioactive elements. Those discoveries helped them earn 2 Nobel Prizes in the early 1900s, and they discovered 2 radioactive elements, radium and polonium. You're going to be watching a little video about Marie Curie and her life. Again, we didn't know about radiation or the long-term effects of radiation. You'll see in the video her hands are very cracked, and that was from handling the raw radioactive materials. Today, if somebody has to handle something that's radioactive, they're going to be wearing pretty much a spacesuit. Their protocol was to wash their hands and change their lab coat. So a lot of it is we just didn't know. Now, Marie Curie, you've heard of her for a couple of reasons. One is she was an important female and that played a very important role in the development of a branch of chemistry. Part of my responsibility in teaching you guys is to point out that underrepresented groups, and when we look at the history and the scientists of the past, do include those unrepresented or those underrepresented groups like women and minorities. Marie Curie did play a massive role in the development of nuclear chemistry. She made the decision to share her results, and that is an important part of science. Everybody didn't have to make the same mistakes as she didn't have to go through the same processes. Once she discovered something and learned something, she would share it with anyone who asked for it. And that really propelled the science to go much, much further, much, much faster than any other branch of chemistry. All right. Now we're going to look at some different types of radioactive decay. Radioactive decay when we have an unstable nucleus. An unstable nucleus consists of protons and neutrons that are just not in the right ratio. small atom to be a stable nucleus has to have a 1-to-1 proton to neutron ratio. So carbon 12, which is number 6 on the periodic table, it has 6 protons, and if it's carbon 12 and 12 is its mass, then it has 6 neutrons. Let's write that up there. So carbon 12, this is hyphen notation, and that's its mass, which is its protons plus its neutrons. And if we look on the periodic table, we can see that the atomic number of carbon is 12. So that means 12 protons, and you take 12 minus your 6 protons, and that gives you 6 neutrons. So that's a 1-to-1 proton to neutron ratio. Now, carbon 14, on the other hand, carbon 14 has a different mass. It's still carbon, so it still has 6 protons. If it's carbon, it's got 6 protons. That's what determines what the element is. So the number of neutrons, that would be your mass minus your protons, and so 14 minus 6 is 8 neutrons. So this is not a 1-to-1 proton to neutron ratio, and so this one is radioactive. One of the common threads through chemistry is that things want to become more stable. And when we have this unstable nucleus, this particular atom is going to try and become more stable, and it's going to do that through radioactive decay. The nucleus is going to emit things, give off things, in order to become more stable. So we're going to look at those types of things. All right. So we're going to make a little table here. I think there are 5 different types of radioactive decay. We'll talk about their symbols. And for certain ones, we will talk about what they can be stopped by, or their penetrating power. The first one we're going to talk about is an alpha particle. An alpha particle is represented by a helium atom. It is not necessarily a helium atom. It is 2 protons and 2 neutrons. 2 protons, now this is nuclear notation, and in nuclear notation, the number that is down here, in this case it is a 2, is the number of protons. And this is stuff we've already gone over. It provides a nice review for that common exam we're going to have next week. And up here is the mass. And then again, that is your protons plus your neutrons. All right, so in alpha decay, it is 2 protons and 2 neutrons. 2 plus 2 gives you that 4 for the mass. Now, alpha particles cannot penetrate very far. They can't get through a sheet of paper, so they have very low penetrating power. Beta, on the other hand, can be represented by this Greek letter beta, and that just is a B that you start kind of low with. -1, 0. The state might also use this one. We'll talk about exactly what happens in beta decay, but any of those. And alpha and beta are the 2 you must memorize for that common exam. It's not given to you. Beta particles can go through a sheet of paper, but they can't go through a piece of aluminum foil. So they have a little more penetrating power than an alpha particle. But still, again, it can be stopped by a block of wood or something like that. Positron emission. Positron emission looks a lot like a beta, except it is positive, hence the name positron. Electron capture is another weird one. It looks exactly like a beta if you write it with an E instead of a B, but it is going to occur in a different location than all the others in our radioactive decay equations. And we'll look at that here in just a minute. And gamma rays. Gamma rays are extremely destructive forms of electromagnetic radiation. Excuse me. It's given off by the sun and those types of nuclear reactions that go on there that provide us with heat and light. They do provide, they are extremely destructive on a molecular level. We're luckily protected from these gamma rays, or gamma radiation, by the Earth's magnetic field. and a lot of times the symbol, I couldn't really find the best symbol on the computer, but it looks like this, maybe like a fish swimming down. We're not going to talk about what it's made up of. Again, it's a wave. Now, gamma rays have the most penetrating power. They can only be stopped by thick layers of lead and or concrete, and you'll see that's how we reinforce some of our nuclear reactors. We'll talk about that in a couple of days. All right, so these are types of radioactive decay. This is what atoms will give off in an effort to become more stable. I talked about small atoms and carbon. Larger atoms, and stable nucleus is a 3:2 neutron to proton ratio, and anything outside of that ratio, the atoms are going to be radioactive and undergo radioactive decay. All right, let's look at each of these types in a little more detail and learn how to write these reactions. So alpha decay. What happens is two protons and 2 neutrons are given off. So if we're going to write the equation, this is in nuclear notation. We've talked about what each of those mean. This is a decomposition reaction, so we only have one reactant. This is uranium-238, and what's going to happen is this is an unstable nucleus. It is going to decay. It is going to give off an alpha particle, and this is just one that we have to know. Alpha particle is represented by a helium atom, and 2 and 4. Now, you always start with the bottom number. Now, it's going to give off this alpha particle, and then uranium is going to actually change into a different element. And this is different from any other chemical reaction that we have talked about. We've never messed with the number of protons because that does change the identity of that atom. And changes it into something else, and we have a nice word for that we'll get to here in a little bit. But they are going to be changing into other atoms with different identities. So we're going to look at this bottom number first. So it's easy to do it this way. What plus 2 gives you 92? And that would be 90. Okay, so we start with that bottom number first. Now 90, that is the atomic number. Now we're going to look on the periodic table, find 90. It is in the actinide series, TH. So that's thorium, named after the Norse god Thor. And then we do the top number. So what plus 4 gives you 238? And that would be 234. Now I have these dashes here because I'm not here to show you what I'm pointing at. Let's see, 234, 90, there we go. And that is a proper nuclear decay equation. You have to figure out what these substances are. Okay. So the atomic mass decreases by 4 and the atomic number decreases by 2. Now let's talk about beta decay. In beta decay, a neutron is converted into a proton and an electron. Now, this statement makes it seem very, very simple, that a positive proton and a negative electron get together and make a neutron, and so a neutron decomposes into those. It's not exactly that simple. It's a nice way to think about it, but remember, protons and neutrons are created by quarks, which are smaller subatomic particles. So it's a recombination of the quarks. All right. But we'll deal with it and think about it this way. So we have thorium, and this guy is going to undergo beta decay. So it is, excuse me, a decomposition reaction. So we'll start, and this thorium atom is going to give off a beta decay. I'm going to use what the state might use, E -1, 0. And we got to figure out what thorium is going to change into. So what minus 1 gives you 90, and that would be 91. Be careful with beta decay. Go back and check. 91 minus 1 does give you 90. Then we look on the periodic table. This is also in the actinide series. And we're talking about protactinium, PA. It's a fun one to say. Now, we're not going to have any change in mass. Now, the reason we don't have a change in mass, remember that a neutron is 1 AMU, and that's the thing that's breaking down. But it's converted into 1 proton, which has a mass of 1 AMU. So we lose 1 AMU and gain 1 AMU, so we don't have a change in mass. That really only happens with alpha decay. All right, so what plus 0 gives you 234? 234. And so that's how you write a beta decay equation. Atomic number increases by 1 and the atomic mass stays the same. All right, we'll span the pages here. Positron emission. A proton is converted into a neutron. This one looks a lot like a beta, except it's positive. So oxygen is going to emit a positron, so that's positive 1, 0. And then we need to figure out what this is going to change into. What plus 1 gives you 8, and that is going to be 7. And so we have nitrogen here. And the mass is not going to change. So with positron emission, atomic number decreases by 1, and the atomic mass stays the same. Again, we lost 1 AMU with the proton, gained 1 AMU with the neutron, so no loss in mass there. Now, electron capture. An electron is pulled into the nucleus. Like I said a few minutes ago, the electron, this one is a little different than the other decay equations that we were working with. Electron capture, what happens is an electron is pulled into the nucleus, combines with a proton to form a neutron. Now, that again, that is a little oversimplification, but it does give us a nice way to think about it. With this one, electron is being captured. That means it is going to be on the reactant side. This is the only one that's like that. -1 and 0 looks just like that beta, except it's on the reactant side. And then you can just read it the way it's written. 11 minus 1 gives you 10, so we're dealing with neon here. And then it's going to be 22 for its mass. We don't have a change in mass. So the atomic number decreases by 1, and the atomic mass stays the same. All right. We're not going to look at equations with gamma, but do know that they do have the highest penetrating power. Now, I told you we'd talk about this word where we've seen these atoms change into atoms of other elements. It's like the dream of alchemy is back, and alchemy is where we were trying to make lead into gold. We can make things into other things. They just happen to be radioactive. And it's called transmutation. And then it's a change in atomic number. Mutation, you should know that that is going to be a change. And we're changing to another atom. So an atom changes from one element to a different element because of radioactive decay.